Hello dear students, welcome you all. In this lecture, I am going to discuss a very important problem, or we can say puzzle of high energy physics, right? And the puzzle is the tau theta puzzle, right? So in this lecture, I am going to explain what is tau theta puzzle and how does it originates, and what was the final solution of this puzzle, right? So if we go back in the history, then in 1950, right? In 1950, right? When we were observing the decay modes of different elementary particles, it was found that uh, we have a particle, right, that we at that time were representing as tau positive, and we have another particle that which were representing as a theta positive. Now these two particles, tau and theta, they were identical in all respects. I mean, they have a same mass, same charge, right? And they were produced by the same type of interactions. They have same, lifetime. But the problem was that these two particles have different decay modes. The one particle that is tau positive, it was decaying into three pi mesons, pi positive, right, and pi positive and pi negative, right? Whereas theta positive was decaying into pi positive and pi naught. So now this was a very big problem in physics, right? If these two particles are identical in all respects, right, they should have same decay mode. And beside to this decay mode, when we were testing the parity conservation here, right, we were observing that these two states that we are getting after the decay, they were having different parity, right? They are different parity states. So it means if we have two particles which have all same properties, what their parity, when they were decaying, the parity was violating, right? The parity was not same in both the decay modes. So this problem at that time was named as a tau theta puzzle, right? Now if we look at the pi mesons, right, we know pi meson, pi positive, pi negative, and pi naught. These are the three types of pi mesons, right? Now we know very well that pi mesons have spin 0 and they have a odd parity. They are representing as a 0 negative. This is their spin parity state, right? They have odd parity and their spin is 0. They are pseudo scalars, right? Now if I want to calculate the parity of this two pi mesons, right? This one I am taking first, this one, then parity of two pi particles, that will be equal to parity of first particle, right, into parity of second particle, right? It is pi 1, it is pi 2, right, into minus 1 power uh, orbital angular momentum of first particle with respect to second particle. So this is the expression, formula that we use for the calculation of parity of the multiple states. When we have multiple particles together, then if we want to calculate the parity of the multiple states, then this is the formula: parity of the first particle into parity of the second particle into minus 1 power orbital angular momentum of first particle with respect to the second particle. Now, as I told you that the parity of pi mesons is negative, so minus 1 into minus 1 into minus 1 power L and orbital angular momentum of first particle. This is the, so what I got? I got minus 1 power L 1 comma 2. So this is the parity of this final state, 2 pi mesons, right? Now let's check the parity of the first case, that is 3 pi meson states. Now when I come to this, then parity of pi, pi and pi. 3 pi particles we have, and their parity will be equal to parity of pi 1 into parity of pi 2 into minus 1 power orbital angular momentum of first particle with respect to second particle. This is the formula, multiplied by, now we have one more particle, parity of third particle, right, multiplied by minus 1 power orbital angular momentum of third particle with respect to first and 1 2 comma 3. This, what is the meaning of it? The orbital angular momentum of the third particle with respect to the first two particles, right? Now again the same logic, parity here, it is first particle is negative, right, it is minus 1, right, it is minus 1, right, it is minus 1, right. So here I got plus 1, right, plus 1 into this one, then minus 1 into this one. So finally I got minus from here into minus 1 power L parity of, let me change the color, parity of first part orbital angular momentum of first particle with respect to second, plus orbital angular momentum of third particle with respect to first two particles. So this is the parity of the final state when this particle decay into 3 pi mesons. Now you can see here that this is equation number 1 and this is equation number 2. I took the parity of the final states from here. We have two decay modes. We are considering that these two different particles are there, right? And one particle is named as tau positive, other is named as theta positive. Why we are doing this? Because these two particles have different decay modes, that's why we are naming them different. Otherwise they have all same properties, right? But again I am repeating that the question is same. If they have all same property, so why it is not a single particle? Why we are treating this as a two different particle? So we are treating it as a two different particle because the parity that we are getting in this reaction, that is different, right? So at that time it was not thought that the parity can be violated in a decay mode. At that time we were thinking that in any reaction, high energy reaction or nuclear reaction, parity is always conserved, right? The violation of the parity was not tested at that time. So that's why we are thinking that these are the two different particles. That's why they have a different parity states, right? But if at that time somebody have thought that parity can be violated, then obviously then it would not be two different particles, but rather it would be a single particle, right? So now we got these two equation number 1 and equation number 2, right? Now we know very well that if I look at the theta positive, right, theta positive, this is theta positive particle. I am starting with theta positive. Now the total spin of the theta positive, that is I am representing as a J, right, theta positive particle, right. Now the total angular momentum that we know of this theta positive particle, J means total angular momentum, that should be equal to, if the law of conservation of angular momentum hold good in this reaction. I am taking this reaction first. Let me write it here. Theta positive, that give you pi positive plus pi naught. I am considering this reaction, this one, right, theta positive. Now if the law of conservation of angular momentum hold good here, right, then what should we get? The total angular momentum of this side should be equal to total angular momentum of this side. Now the total angular momentum includes both spin angular momentum as well as orbital angular momentum. Now here these two particles have spin angular momentum 0. I told you in the beginning that they have spin 0 and parity negative. So it means their total orbital angular momentum, that is L 1, 2, it should be equal to the total angular momentum, or we can say spin of this particle, theta positive, right? Similarly, in case of tau positive, then we have three states, right? The pi positive, and pi negative, right? In this case also we should get what? The total angular momentum of this side should be equal to angular momentum of this side. So again, J of tau positive, that should be equal to, right, orbital angular, total orbital angular momentum, because spin angular momentum is 0. So total orbital angular momentum, first particle with respect to second plus first second particle with respect to third. So this is the thing that we should get from here, right? If the law of conservation of angular momentum hold good, right? Now I'm coming back to here, right? These two equations, equation number 2 and equation number 3. Let this is equation number 3 and this is equation number 4. So if I put this equation number 3 in equation number 1, right, then what I got? Parity of pi 2 pi mesons, that should be equal to minus 1 power j theta positive, right? And similarly, parity of 3 pi mesons, pi. You can even write in this case it is pi positive and pi naught, or pi positive, pi negative. It is your choice. Then it should be equal to minus 1 power, what was there? Minus 1, minus into minus 1 power, minus was also there, minus into minus 1 power j, what? It is a tau positive, right? So this is the parity of the final state. Now if parity is conserved in these reactions, then I can write that this should be equal to parity of theta positive, and this should be equal to parity of tau positive, or you can write, right? So in this way now I can write it further, p theta positive, that should be equal to minus 1 power j theta positive, right? And parity of tau positive, that should be equal to minus into minus 1 power j tau positive, right? Now it has been measured experimentally that this j theta positive is equal to j tau positive, this is equal to 0. If I put 0 0 here, then what I should get? I should get from this equation that this is equal to minus 1 and this is equal to plus 1. It means these two particles, right, that is theta positive and tau positive, they have different parities. One have odd parity and other has even parity according to these reactions decay modes. So these two particles cannot be identical, but again the problem is there that these two particles are totally identical, same mass, charge, lifetime, and produced by the same interaction, right? So as we are getting different parity of the particle, that the two particles that appears to be same, so it was a great puzzle in physics, right? At that time it becomes a puzzle that why we are observing this, why we are getting different parity for the two particles which are otherwise same, right? And that's why these two particles were defined. One is defined as tau and other is defined as theta, right? So it was $1 million question at that time, biggest puzzle, right? So this puzzle was removed in 1956 by T.D. Lee and C.N. Yang, and up to till that time it remains a big puzzle or a problem in physics. So in 1956, right, a group of physicists, T.D. Lee and C.N. Yang, right, they performed the experiment and they checked the parity conservation in weak interactions, because prior to that nobody have checked the conservation of parity in weak interactions, right? Although people were skeptical about the conservation of purity in weak interactions, but no experiment has been invented till that time that can check the violation of purity conservation in weak interactions. So T.D. Lee and C.N. Yang were the first person who checked the tested the conservation of purity in weak interactions. Why we did that? Because this decay mode was weak. The interaction under which this reaction was taking place, that was a weak reaction, right? Weak interaction. So we should have knowledge that what happened to purity in weak interactions. So when they measure the purity check the purity conservation in weak interactions in 1956, right? They found that purity is violated in weak interactions, right? It is not conserved, right? Based on their theoretical predictions, Wu, C.S. Wu, we will discuss it in the coming lectures. W. Wu, he performed C performed an experiment. Sorry, in 1956 on cobalt 60, on the decay of cobalt 60, and he confirmed that purity is 100% violated in weak interactions, right? And that experiment then confirmed that these two particles are not different particles. What they are, that two particles are basically the same particle that has two different decay modes, and in two different decay modes we are getting a different purity because purity is not conserved, right? So as this experiment performed by C.S. Wu confirmed that the purity is 100% violated in weak interactions, so immediately after that it becomes very clear that this, the puzzle that were considering this as a puzzle, that these are two different particles. Now this problem was solved and it was confirmed that these are not two different particles, but they are a same particle, kaon, K positive. That this particle is known as a kaon, right? And in this this particle that is showing these two different decay modes, it is kaon positive, K positive, and now this particle is at present known as a kaon K positive, right? So this was the tau theta puzzle, and this puzzle was solved by performing experiment to check the violation of purity conservation on weak interactions, and that weak interactions that experiment confirmed that the purity is violated. It is not conserved in the weak interactions. We can get different purities with the same particle in different decay modes. So this problem is solved in this way. So in the coming lecture we will discuss this T.D. Lee and C.N. Yang and C.F. Wu experiments in detail that has confirmed this. Later on, after this experiment, many other experiments confirm the same thing, and at present we know very well that purity is not conserved in weak interactions, right? So this is all about the tau theta puzzle. So thank you very much.